Elon Musk admitted.
It's a very hard problem to solve. You have to design every part of it from physics first principles. There's nothing that's off the shelf that actually works.
When referring to the challenge of creating the robot's frame, therefore Tesla developed the frame for Optimus themselves, using magnesium priced at $2,800 per ton, combined with advanced casting technology. The result is the ultra-light frame of Generation 3.5, which helps save costs and improve performance. So, what is the secret that enabled Tesla to achieve this important breakthrough? Before we begin, please help us reach 15,000 subscribers. It will be a huge motivation for us to continue bringing you great episodes about Tesla Bot, Tesla EVs, and the latest news. How does the ultralight frame help Tesla reduce costs and streamline mass production? The ultralight frame is one of the key factors determining the success of Tesla Optimus Gen 3.5 in mass production. In the humanoid robot industry, reducing weight while maintaining the durability and stability of the frame is a major challenge. Tesla has addressed this issue by choosing magnesium instead of aluminum as the material, combined with advanced manufacturing technology and standardized design, helping reduce raw material costs, shorten production processes, and improve the robot's operational performance. The biggest innovation in the Optimus Gen 3.5 frame is the use of magnesium to replace traditional aluminum. In the Chinese market, where Tesla sources its supply, magnesium costs about $2,800 per ton, approximately 10% cheaper than aluminum, which is about $3,100 per ton. Although this price difference seems small, when multiplied by the large amount of material required to produce thousands of robots, the total cost savings become significant. Not only is magnesium cheaper, but it is also about 30% lighter than aluminum. This means Tesla can reduce the amount of material needed for the frame, thus lowering the robot's total weight. Weight reduction not only saves raw materials, but also enhances operational efficiency by reducing energy consumption and extending component lifespan. To fully leverage magnesium's properties, Tesla applies thixomolding technology, a semi-solid metal casting process that is advanced in the metal casting industry. This technique allows faster and more precise molding, reducing the number of complex machining steps compared to traditional casting methods. Studies show that thixomolding can reduce material waste by 20% to 30%. This means Tesla saves a large amount of raw material while shortening processing time and increasing production capacity. Applying thixomolding also lowers production costs and speeds up frame completion, a prerequisite for mass-producing thousands of robots in a short time. Beyond material and casting technology innovations, Tesla focuses on standardizing components to simplify the production process. The frame of Optimus Gen 3.5 is made from aerospace-grade aluminum alloy, combined with lightweight polymers. However, instead of using hundreds of component types like other robot models, Tesla uses only 6 customized actuators for the entire robot. This standardization significantly reduces design, assembly, and maintenance costs. At the same time, it helps synchronize production lines and easily scale up to produce millions of units. Standardizing components also shortens staff training time and minimizes errors during production, improving the product qualification rate. A crucial part of Tesla's production strategy is optimizing the magnesium supply chain. China dominates global magnesium production, providing Tesla with abundant and stable-priced raw materials. Switching to magnesium allows Tesla to avoid dependence on aluminum sources, which are expensive and highly volatile on the international market. A stable supply chain combined with low raw material costs helps Tesla easily achieve its goal of producing 5,000 to 10,000 Optimus Gen 3.5 robots in the first year. This creates a major cost advantage and ensures uninterrupted production plans without raw material shortages. Thanks to improvements in materials and design, the weight of Optimus Gen 3.5 is reduced to about 125 pounds, compared to 132 to 154 pounds in previous versions. Although only reduced by a few pounds, the impact of weight reduction is significant. A lighter robot consumes less energy during operation, extending working time per charge. This not only lowers operating costs, but also increases efficiency in practical applications. Moreover, lower weight reduces mechanical wear and tear, prolonging component lifespan and decreasing maintenance and replacement costs during use. A lighter weight also means Tesla can design production lines and transport with lighter lifting equipment, saving factory investment costs. The combination of magnesium material, Thixa molding technology, and component standardization has created an ultra-light frame that is cost-effective, easy for mass production, and efficient in operation. This is not only a technical breakthrough but also a comprehensive economic strategy that helps Tesla enhance its competitive edge in the promising humanoid robot market. In the future, as Tesla scales production to hundreds of thousands or millions of robots, advantages in raw material costs and production processes will become even more critical. The ultra-light frame is the foundation for Tesla to optimize manufacturing while improving robot performance and durability, thereby meeting increasingly stringent market demands. Additionally, weight reduction supports energy systems and control software to operate more efficiently. A lighter robot requires less energy to move, meaning batteries can be designed smaller or operate longer without increasing size or weight. This significantly improves user experience and the practical application potential of Optimus Gen 3.5 in industrial, service, and healthcare environments. Once again, please help us reach 15,000 subscribers. This is important for us to stay motivated. Thank you. How does the low weight optimize energy efficiency and extend component lifespan in Optimus Gen 3.5? The ultra-light frame is not only a technical breakthrough, but also the golden key that enables Tesla Optimus Gen 3.5 to significantly expand its application range and firmly establish its position in the global market. While many competitors still struggle with heavy and bulky frames, Tesla has wisely chosen the path of weight reduction to deliver flexible, safe operation suitable for a wide variety of environments, something not every humanoid robot can achieve. In practice, robots with lighter frames adapt much more easily to complex and restricted working environments. For example, heavy industrial robots are often limited when moving through narrow spaces or working on weak flooring. Whereas Optimus Gen 3.5, weighing only about 125 pounds, is completely different. It can maneuver lightly through narrow aisles in factories or crowded offices, something that competitors with robots weighing 154 to 176 pounds must be cautious about. Thanks to this, Tesla expands its application capabilities from manufacturing plants to customer service and even to healthcare and home assistance, fields that demand extreme delicacy and safety. Compared to traditional robots, Tesla's ultralight frame also significantly reduces the risk of collision, an ongoing headache for the humanoid robot industry. A robot weighing up to 176 pounds can cause serious injury upon impact, while Optimus Gen 3.5, with nearly 30% less weight, greatly reduces this risk. This is why Tesla not only targets industrial applications, but also confidently ventures into healthcare, where safety and reliability are paramount. Users can feel more secure, having a robot friend that is gentle and non-threatening in everyday support tasks. Furthermore, the lightweight design helps Tesla substantially reduce transportation and installation costs, thereby improving its ability to scale in the global market. Transporting a 154-pound robot compared to a 125-pound one means a significant difference in logistics expenses, especially when shipping thousands of units via sea, air, or land routes. Tesla leverages this advantage to quickly expand its distribution network, lower prices, and effectively deliver products worldwide. While many competitors still struggle with high shipping costs, Tesla already holds a competitive edge starting from this stage. The ultra-light frame also provides a foundation for exceptional flexibility in integrating new features and expanding customization capabilities. While some other robots face constraints in weight and size that make upgrades difficult and costly, Tesla's lightweight frame easily makes room for additional modules such as sensors, cameras, or specialized tools. This enables Optimus Gen 3.5 not only to be versatile, but also ready to adapt intelligently and flexibly to diverse tasks, from industrial automation to personalized human care. Another important highlight is that the lightweight frame contributes to enhancing the product's sustainability value. Using magnesium materials combined with advanced manufacturing technologies significantly reduces material waste and energy consumption throughout the robot's life cycle. While many robot manufacturers have yet to prioritize environmental factors, Tesla has pioneered building a more planet-friendly product, an approach that not only strengthens a TU brand image, but also aligns with global sustainable development trends. Finally, the ultra-light frame helps Tesla design a robot that is not only intelligent, but also sleek and modern, an element that cannot be overlooked in the fierce competition of the humanoid robot market. Compared to other humanoid robots with bulky appearances, Optimus Gen 3.5 stands out with its refined look, making it easier for users to accept and trust. The combination of a lightweight design with superior performance is the formula that helps Tesla make a lasting impression in the increasingly competitive humanoid robot market. How does the low weight increase the safety of Optimus Gen 3.5? The ultra-light frame is not only a technical breakthrough, but also the golden key that enables Tesla Optimus Gen 3.5 to significantly expand its range of applications and firmly establish its position in the global market. While many competitors still struggle with heavy and bulky frames, Tesla has wisely chosen the path of weight reduction to deliver flexible, safe operations suitable for diverse environments, something that not every humanoid robot can achieve. Compared to traditional robots, Tesla's ultralight frame also significantly reduces collision risks, a constant headache for the humanoid robot industry. The low weight of Tesla's Optimus Gen 3.5 actually makes it a lot safer to be around. Because it's lighter than most humanoid robots, there's less force if it bumps into you, trips, or even falls over. That means if you're standing next to it in a factory or at home, you're far less likely to get hurt compared to being near a heavier machine. A lighter frame also means it can react faster if something suddenly gets in its way. It can stop or move aside more quickly, avoiding accidents before they happen. This lower weight also takes a big load off its joints and motors, so it's less likely to break in a way that could cause trouble. And because it doesn't carry as much mass, it's easier for the robot to keep its balance. Even if it does lose footing, the impact is softer and less damaging to anything or anyone nearby. Tesla's use of strong but lightweight materials, like advanced aluminum and carbon fiber, also helps keep the robot cool during long shifts. That's another quiet safety win. Overheating parts are less of a risk when the body is lighter and more efficient. In short, the lighter build isn't just about making Optimus faster or more agile. It's about making it a safer teammate for people to work alongside every day. Tesla is moving closer to a pivotal milestone in robotics: the launch and commercial debut of the Optimus Gen 3.5. This upgraded humanoid robot is not just an incremental step from its predecessors. It represents a significant leap in readiness for real-world deployment. While Tesla has showcased earlier prototypes performing factory tasks, the Gen 3.5 is designed with refined mechanics, lighter materials, improved dexterity, and a more efficient power system, all aimed at making it viable for broader industrial and domestic applications. Elon Musk has hinted that this version will bridge the gap between testing and mass adoption, signaling that the company is preparing to open orders sooner than many expected. According to Musk, Tesla is on track to start limited deliveries of the Optimus Gen 3.5 once final testing in its own factories confirms the robot's reliability and cost-effectiveness. This aligns with Tesla's long-standing approach, using its factories as both proving grounds and training environments, ensuring the robots are fully prepared before reaching customers. Early deployment will likely target Tesla's own production lines and select business partners, allowing the company to gather performance data in diverse, high-intensity settings. Musk's strategy here mirrors how Tesla ramped up the Model 3, starting with controlled rollouts before scaling globally. The Gen 3.5's planned launch is also tied to significant production ramp-up goals. Tesla has already been building a dedicated assembly process for Optimus within its existing gigafactories, with a capacity to produce thousands of units annually once operations stabilize. Musk has stated that the company's medium-term vision involves producing over 10,000 units per year in the US alone, but the Gen 3.5 will serve as the essential launchpad for that scale. By perfecting manufacturing on this version, Tesla can reduce costs and refine supply chains ahead of future iterations. This launch will mark the first time a Tesla robot becomes available to customers outside of internal use, setting the stage for mass-market adoption. While Musk has not confirmed the exact launch date, the tone of recent updates suggests that an official reveal and order opening could happen within the next year. The Optimus Gen 3.5, therefore, is not just another prototype. It is the product Tesla intends to sell, the model that will begin transforming humanoid robots from futuristic concepts into practical tools for work and everyday life. The headline sounds like clickbait until you trace the engineering. Hidden tech really can make Tesla bots seem like it thinks. Tesla Optimus version 3.5 is not suddenly conscious, but its behavior can cross a threshold where perception, prediction, and planning happen so quickly and coherently that to a human it feels like intention. So what gives Tesla Optimus the ability to think? Don't click away. In the next 30 seconds, I'll show you Tesla's most secret update about Optimus. Before we begin, if you love staying ahead on Tesla and AI tech, hit subscribe now. You'll be the first to know the breaking news. The Vision Stack ingests and interprets the world at 1,000 frames per second, while fusing a 32-megapixel multispectral camera with a depth system that resolves down to 0.1 millimeters. A typical person needs about 200 milliseconds to register a visual stimulus and produce a reaction. Many industrial robots running camera-in-the-loop control still live near 100 end-to-end. If Optimus holds sensor-to-actuator latency below 10 milliseconds for common tasks, it is roughly 20 times faster to respond than peers that operate in 200 millisecond budgets. And the difference is visible. Hitting 1,000 Hz with a meaningful signal requires a hybrid pipeline. The 32-megapixel multispectral camera supplies high-detail frames that anchor texture, color, and fine alignment, even at 10 bits per pixel, which is 320 gigabyte per second, far beyond what you would sling across a general bus. So the camera head pushes intelligence to the edge. The last leg of the perception stool is temporal. Seeing faster is not the same as understanding sooner. The Optimus pipeline, therefore, keeps a short-term buffer of microframes and a medium-term buffer of world states. The short buffer runs at 1,000 Hz for contact-rich actions, such as grasping, pouring, or foot placement on variable terrain. It feeds jerk-limited controllers with fresh surface normals and slip estimates every millisecond. The medium buffer ticks at 120 Hz and feeds a world model transformer that reasons about objects, humans, and constraints across a few seconds. Sight without foresight is twitchy, so Optimus borrows the best ideas from Tesla's full self-driving program and repackages them for bipedal life. Two ingredients stand out. The first is occupancy and semantics in 3D, learned end-to-end from video. On roads, occupancy networks infer drivable space and the intent of agents. Indoors, they infer traversable regions, affordances like handles or latches, and the likely motion of people or carts. The second is planning with a learned cost that can look further ahead than hand-coded rules. A humanoid does not need to forecast 100 meters down the freeway, but it does need to project several seconds into a busy scene, predict where gaps will be near doorways, and anticipate how a human coworker will reach for a shared object. If the Tesla Optimus brain genuinely carries 10x more parameters than the prior release, think of the leap not as raw bloat but as representational headroom. More capacity for rare configurations of limbs and props, more nuance in human pose estimation, more memory for the oddities of cupboards, drawers, and carts that were underrepresented in earlier data. What engineering unlocks at home, and especially for older adults? Far-field voice wake works across typical living rooms at up to 5 meters with beamformed microphones that hold a 20 to 30 decibel signal-to-noise margin, even with TV audio in the background, so an older adult does not have to shout to be heard. Low-light navigation remains stable, which means nighttime trips to the kitchen require no harsh lighting, because the light in the RGB strip will ignore the ambient light factors for the robot. Moreover, door handles, faucets, and appliance knobs are treated as affordances rather than custom scripts, so a new kettle or a different fridge handle still makes sense to the robot after a few seconds of observation. In daily routines, this translates to real tasks, carrying 15-pound grocery bags from the door to the counter without banging into corners, loading or unloading a dishwasher. When looking at safety supervision for aging in place, slip and fall signatures are detected in under 100 milliseconds from body pose and acceleration cues. The local response begins immediately by reducing nearby actuator torques and clearing space, while a parallel network triggers alerts. If the person is responsive, the robot requests verbal confirmation and offers a handhold at a safe height within 2 seconds. If there is no response, Tesla Optimus will immediately notify the authorized caregiver. To avoid false alarms during normal lounging or stretching, the planner demands a multi-signal agreement, pose, motion, and audio, before calling for help, and it asks a simple word confirmation first, when possible. Medication adherence becomes less about smart pillboxes and more about embodied routine. At scheduled times, Optimus arrives with water and a reminder. A small on-wrist camera verifies that the cap on the corrected vital is opened. A top-down view checks count and color without storing images beyond the event, and a local model marks the dose as taken. If the person hesitates, Optimus will offer a read-aloud explanation, repeat dosage, and can place a caregiver call on request. Additionally, telepresence is built into the same head unit that reads the world. A stabilized eye-level camera keeps remote family at natural height, while a 3 microarray captures clear speech. Echo control is tuned for small rooms so older voices do not get lost. A call can be initiated in under 10 seconds by voice or by a single large target tap on the chest display, and can be routed to a short list of trusted contacts. For check-ins, the robot can perform a 60-second wellness sweep, temperature with a non-contact sensor, room CO2, open window state, stove state, then report a simple green or yellow status to family, with full details only visible locally. So when someone asks how Optimus can think, resist the tug toward mysticism. The answer is that it sees faster, with more reliable measurements, and it uses that stream to predict a little further and a little better than you expect. It plans continuously instead of in lurches. It treats contact as a signal to be shaped, not a surprise to be endured. It learns from its own near misses and from a planet of sister machines that did something similar yesterday. It accepts new hands and new souls, the way a person accepts new tools or shoes. And because it is built on the shoulders of a driving stack that already learned to reconcile messy video with stubborn physics, its priors are good from day one. None of this makes it a person. All of it makes it a partner that appears to think because it almost always does the next right thing without drama. The promise of Optimus is not a one-time leap to artificial general intelligence. It is the crystallization of an approach. Crank the perception loop to 1000 Hz where it matters, anchor it with a 32-megapixel multispectral eye, and a 0.1 mm depth sense for trustworthy geometry. Widen the brain by about 10x so it can remember and generalize, and wrap it in a body that can be repaired, upgraded, and specialized in minutes. Do that, and a 6-foot machine begins to behave in ways that humans read as thought. It is less about what's philosophically inside, and more about what is practically inside. A data-sane camera head instead of a fire hose, a world model trained on a million small truths, a planner that looks a few seconds ahead and never panics, actuators that can whisper torque every millisecond, and modules that come off with a quarter turn. That is how hidden tech becomes visible as competence. That is why Optimus can seem to think. How does Tesla Optimus's brain work? How is it superior to humans? The structure of Optimus's AI brain begins with Tesla's long history in autonomous driving. For over a decade, the company has trained its cars to recognize lanes, pedestrians, traffic signals, and complex road scenarios using 1.5 billion miles of driving data. That knowledge provided the baseline for how a humanoid robot could learn to see the world. 8 cameras mounted on Optimus, with a combined resolution of 16 megapixels, feed high-bandwidth streams at 120 frames per second into a cluster of Tesla-designed AI chips. These are not off-the-shelf GPUs, but custom dojo-like architectures optimized for low-latency decision-making, achieving 1.2 trillion operations per second with a power draw of 250 watts. At the lowest level, convolutional neural networks parse raw pixels into edges, textures, and objects with 98% accuracy. On top of that, transformer-based models with 12 billion parameters build temporal memory, enabling the robot to anticipate movement patterns, track the trajectories of human coworkers within 0.1 meters, or infer the weight of an object to within 50 grams before lifting it. The principle is simple but revolutionary. The AI brain works not in isolated loops, but as a deeply integrated sensory-motor cortex. Vision is not separate from planning. Proprioception from 128 torque sensors feeds into the same neural net that processes video at 100 Hz. This mimics the way human biology merges sensory input with motor planning. The result is fluid motion. When Optimus reaches for a part on the factory line, its 22 degree of freedom fingers predict micro-adjustments in grip force within 0.01 Newton, because the visual network has signaled potential slippage with 95% confidence. Such coupling of perception and action is a major leap forward compared to earlier humanoids that relied on rule-based control with error rates of 10 to 15%. Deep reinforcement learning provides the second foundation of Optimus's intelligence. Rather than hand-coding instructions for every movement, engineers allow the robot to learn through 15 million simulated trials, rewards, and corrections. In simulation, Optimus performs 10 million pick-and-place tasks, 5 million walking gaits, or 2 million cooperative maneuvers with other robots. Success is encoded as reward signals, while mistakes trigger backpropagation through the network. The sheer scale is breathtaking. Tesla's AI training pipeline processes 2 petabytes of video per day, with Optimus training consuming 500 terabytes daily. In practice, this means Optimus can adapt to new tasks 10 times faster than a human. Where a child might take 6 months to master dexterous hand-eye coordination, Optimus compresses that learning into 48 hours by leveraging reinforcement at industrial scale, achieving a task success rate of 97%. Memory, often overlooked in robots, is crucial for Optimus. A child learns by building an internal model of the world. Optimus uses recurrent networks with 8 billion parameters and vector databases storing 1 terabyte of task data to recall past tasks. When it tightens a bolt with 20 Newton meters of torque, it stores torque values and hand trajectories with 0.05 millimeters precision. The next time it encounters a similar bolt offset by 2 millimeters, it applies the old strategy with minimal adjustments, reducing task time by 30%. This transfer learning gives Optimus continuity across 150 distinct tasks. Unlike earlier robots that reset after every cycle, Optimus accumulates skill. Each hour in the factory adds 500 megabytes of experiential data, making the robot smarter over time. Real-time data processing is another cornerstone. Human cognition processes visual input in under 200 milliseconds. Optimus matches this with a latency of 30 milliseconds, achieved by combining sensor fusion and edge computing. 8 cameras, 4 microphones, and 128 force sensors stream data at 1000 Hz into a central processor. This allows Optimus to hear verbal instructions, interpret them through a speech recognition model with 95% accuracy, map the request to a task library of 10,000 entries, and begin movement within 50 milliseconds. Even in noisy factory environments with 100 decibel sound levels, Optimus filters acoustic signals and synchronizes them with lip motion detection from cameras, reducing ambiguity by 40%. Such multimodal AI ensures Optimus responds as naturally as a trained coworker. Comparison with rivals reveals why Tesla's approach is disruptive. Unitree's humanoid prototypes rely on predefined motor control patterns, achieving only 85% task adaptability. Figure AI has made progress in dexterous manipulation, but its models depend on third-party cloud training, with 200 millisecond latency and lack Tesla's vertical integration of 50 billion miles of driving data, chips, and vehicles. Optimus V3.5 enjoys a unique edge. Its AI is refined from 10 million robot trials and 1.5 billion miles of driving data, with perception models achieving 98% robustness and decision-making tested over 100,000 real-world scenarios. Concrete numbers highlight this advantage. Internal benchmarks show Optimus achieving task learning speeds 10 times faster than traditional humanoid platforms. In controlled trials, a set of 100 assembly tasks that took human trainees 40 hours to master were reduced to 4 hours for Optimus, with an error rate of 1.8% compared to 12 to 15% in rival systems. Real-time inference throughput reaches 1.2 trillion operations per second, while power consumption remains under 250 watts. These figures derive from the scaling laws of Tesla's Dojo supercomputer, applied to a humanoid context. The broader impact of this AI brain extends beyond Tesla. If Optimus can learn 150 tasks in 48 hours, industries will recalibrate expectations. Manufacturing will deploy robots in 3 days instead of weeks. This dynamic capability impacts logistics, handling 200 packages per hour, and elder care, supporting 20 daily tasks. Globally, humanoids could fill gaps in aging populations, with Japan's workforce shrinking by 11% by 2030. Developing economies could deploy Optimus in sectors where training costs exceed $10,000 per worker. Tesla's decision to merge reinforcement learning, deep vision, multimodal processing, and hardware optimization challenges the fragmented approach of academic AI. It demonstrates that intelligence grounded in physical action is robust. Algorithms accounting for gravity, friction, and fatigue become 30% more generalizable than those optimized in digital games alone. This insight will inspire new AI architectures and benchmarks. Tesla will spend more than $500 million to expand its fast-charging network this year. Elon Musk once said, and now Tesla has proven it. Imagine over 1 million Tesla cars and Optimus robots sharing a single charging station. Fast-charging technology allows the robots to recharge 3 times faster than before in just 30 minutes, almost eliminating any waiting time. So, how will Tesla combine charging for both cars and Optimus Gen 3.5? Before we begin, please help us reach 15,000 subscribers. It will be a huge motivation for us to continue bringing you great episodes about Tesla Bot, Tesla EVs, and the latest news. What can a shared charger do for Tesla and Optimus? When Tesla began branching out from electric vehicles into the humanoid robot space with Optimus, an interesting question emerged. How can these two siblings charge in the most compact and cost-efficient way? The most logical answer might be, let them share the same charging system. Sounds simple, but the benefits are far from small. First, there's the matter of money. A 250 kilowatt DC fast charging station, according to ICCT's 2023 report, costs anywhere from $35,000 to over $100,000 to install, depending on location and electrical infrastructure. If Tesla were to go big and build a dedicated network for cars and another for Optimus, costs would nearly double. Suppose a factory needs 10 charging points for cars and 10 for robots, each costing about $50,000, totaling $1 million. But if both cars and robots share the same 10 stations, adding only an adapter and management software, the total might drop to around $550,000. A simple calculation shows nearly 45% savings, and at a scale of hundreds of cars and robots, this is no small figure. Next is the question of space. Each fast charger takes up about 4 to 6 square meters, not counting space, for maintenance and operation. If separate systems were built for cars and robots, the footprint would double. In a factory or warehouse, every few dozen square meters are highly valuable, potentially used for production lines or storage. With shared infrastructure, Tesla could deploy dock-style chargers or even wireless charging pads usable by both vehicles and Optimus. This could cut the charging footprint by half. Operationally and in terms of maintenance, things would also get easier. Data from ChargePoint shows each fast charging station costs roughly $400 to $1,200 annually to maintain. Halve the number of stations, and maintenance costs drop accordingly. Technicians would only need to manage one unified system, reducing confusion and allowing quicker troubleshooting. Tesla's strength in blending software with hardware makes flexible charging allocation easy. For example, during the day, chargers could serve EVs, and at night, Optimus robots. A smart scheduling system could prevent queues and downtime. In fact, the shared infrastructure model isn't new. Airlines share gates and ground services. Logistics firms share cold storage. The goal is always the same: cut costs and maximize resource use. Tesla could do the same, adding automated recognition and dynamic power adjustments for each device type. Of course, there will be challenges. Tesla EVs use the NACS port, while Optimus might require a smaller connector, so adapters or compatible docks would be needed. Cars demand high charging power, 150 to 250 kilowatts, while robots only require a few kilowatts, so software would need to balance loads to avoid overcapacity or waste. When both urgently need power, the system must prioritize without disrupting operations. If these issues are solved, shared charging could become a strategic move, saving money, saving space, and boosting operational efficiency. This wouldn't just optimize today's operations, but would pave the way for Tesla's long-term ecosystem vision, where everything from cars to robots is seamlessly connected and powered. Currently, Tesla has quietly tested prototype charging stations capable of serving both EVs and Optimus robots at some internal research facilities. A source from Fremont revealed the system uses Tesla's NACS standard combined with an automated charging mechanism that connects to Optimus's port without human intervention. This shows Musk isn't just talking about ideas. His engineers have been working on it early to shorten the path to deployment. If successful, Tesla could roll out thousands of these stations at Giga Texas, expected to be the hub for both car and robot production. Economically, shared charging infrastructure could slash costs dramatically. Building two separate systems would double spending on electrical hardware, cables, energy management units, and upkeep. Combining them not only reduces hardware needs, but also lowers staffing and long-term maintenance costs. Internal estimates suggest shared charging stations could cost 35 to 40% less than separate ones, while enabling expansion 1.5 times faster. With 1 million Optimus robots planned in the coming years, the savings could reach billions, a figure no company would ignore. Strategically, Musk aims for an ecosystem where every device, from the Model 3, Cybertruck, and Semi, to Optimus, speaks the same energy language. This reduces costs and locks users into Tesla's ecosystem, much like Apple did with the Lightning charger. Once Optimus drinks from Tesla chargers, customers will be further tied to the brand, needing only one infrastructure to power both vehicles and robots. The long-term vision stretches further. If these charging stations become a global standard, Tesla could allow other robot or EV manufacturers to pay for access. Just as they opened NACS to Ford, Rivian, and others, Tesla could turn the charging network into a steady revenue stream. Every robot or vehicle charging would generate income for Tesla, whether it's their product or not. This is exactly the hardware plus service strategy Musk has often emphasized. An intriguing aspect is priority-based smart charging. For example, at night when car demand is low, stations could prioritize charging Optimus robots so they're ready for work the next morning. During peak morning hours, the system could shift focus back to cars. All of this would be controlled by AI-driven energy management software, optimizing every kilowatt hour to keep all devices running smoothly. Zooming out, shared charging for Optimus and Tesla vehicles is part of Musk's grand connectivity map, where robots, cars, energy storage, and renewables are all synchronized, automatically managed, and waste minimized. This is key to producing 1 million Optimus units without hitting an energy bottleneck. If each robot needed its own charging source, costs and setup times could seriously slow expansion. All of this fits perfectly with Musk's approach at Tesla. Build a common platform, squeeze every bit of value from each dollar spent, and turn infrastructure into a lasting competitive edge. If the plan works, we could see a global network of chargers not just for cars, but as energy pit stops for millions of service robots worldwide. Once again, please help us reach 15,000 subscribers. This is important for us to stay motivated. Thank you. How does fast charging technology from electric cars transfer directly to robots to minimize waiting time? Optimus Gen 3.5 is not just a hardware upgrade. It marks a major leap forward in charging infrastructure and energy management. The key highlight is that Tesla has applied its fast charging technology, originally designed for EVs, to the robot, but refined to meet the continuous operational demands of Generation 3.5. Whereas previous versions required around 2 to 3 hours to fully charge, Gen 3.5 can reach 100% in under 60 minutes. This enables the robot to maintain an almost uninterrupted work cycle, a critical factor as Tesla aims to produce and deploy 1 million units. This charging speed far surpasses many competitors. For example, Figure AI's Figure 02 requires roughly 2 hours of charging for 5 hours of operation, while Agility Robotics' Digit takes even longer, limiting its ability to work long shifts. By contrast, Optimus Gen 3.5 can replenish enough energy for 8 to 10 hours of runtime in just 45 to 50 minutes with a high-power charger. This is a massive advantage for robots working 24/7 in manufacturing or logistics environments. Tesla is also testing an interleaved charging model, in which robots automatically move to the charging station when their battery drops to 15 to 20%, then return to work without human intervention. With a synchronized charging system, 100 Gen 3.5 robots in a factory can rotate between charging and working, boosting overall efficiency by 20 to 25% compared to the previous generation. This not only minimizes downtime but also optimizes operating costs for businesses. Another important improvement is charging station compatibility. Elon Musk has revealed plans for Optimus Gen 3.5 to use the same charging standard as Tesla EVs, NACS, meaning factories, warehouses, or service centers can share charging infrastructure for both electric vehicles and robots. This dramatically reduces upfront investment. Considering that a single fast charging station costs an average of $35,000, shared infrastructure could save millions of dollars when deploying thousands of robots. The Gen 3.5's battery has also been refined for higher energy density, with a capacity of around 2.3 to 2.5 kilowatt hours, but 15% lighter than Gen 3. This improves both charging efficiency and operating time. Notably, Tesla has integrated an active thermal management system to keep battery temperature stable between 20 to 30 degrees Celsius, even during fast charging, extending battery life to over 3,000 cycles, equivalent to more than 8 years of daily charging. Beyond hardware, Tesla's intelligent charging orchestration software plays a decisive role. Gen 3.5 connects to a fleet management system capable of predicting energy demand based on workload and automatically scheduling charging times to prevent station overload. This mirrors how Tesla coordinates superchargers for millions of EVs worldwide, but scaled down and optimized for factory and service environments. From an economic standpoint, Gen 3.5's fast charging capability reduces non-productive time, thereby improving return on investment (ROI) for customers. For example, if a robot loses 2 hours per day to charging, Over 1 year, that's more than 700 hours of lost potential production. With Gen 3.5, that figure drops to under 200 hours, saving tens of thousands of dollars per robot annually, not to mention the impact when scaling to hundreds or thousands of units. The charging technology in Generation 3.5 also opens the door to outdoor and remote operations. Tesla is testing mobile solar-powered charging stations, enabling deployment of robots at construction sites, farms, or areas with incomplete infrastructure. This greatly expands the potential market beyond traditional manufacturing. Clearly, Optimus Gen 3.5's strength lies not only in task execution or agility, but in how Tesla has optimized the entire energy chain, from the battery and charging stations to intelligent scheduling software. By combining fast charging infrastructure sharing with EVs and automated charging coordination, Gen 3.5 becomes the only robotic platform today capable of continuous operation at million-unit scale. This positions Tesla for absolute market leadership, turning charging technology into a strategic lever for dominating the global robotics industry. Why manage energy between Tesla and Optimus? One of the most overlooked yet transformative innovations in Tesla's ecosystem is its intelligent energy management system, which seamlessly allocates electricity between electric vehicles and Optimus Gen 3.5 robots. This technology is not just about charging. It is about creating a unified energy network where power flows intelligently to wherever it is needed most, ensuring maximum operational efficiency. At the heart of the system is Tesla's proprietary software platform, originally developed for balancing power distribution in large-scale supercharger networks. In the past, this technology was primarily used to manage high-demand EV charging stations, ensuring each vehicle received the optimal current without overloading the grid. With Optimus Gen 3.5 entering the picture, Tesla has adapted this capability to manage two fundamentally different but equally energy-dependent products: cars and humanoid robots. The intelligent energy management system constantly monitors battery health, charge levels, and usage patterns of both the EV and the robot. For example, if a Tesla Model Y in a household is at 80% battery capacity and an Optimus Gen 3.5 is running low at 20%, the system can automatically prioritize sending more electricity to the robot without manual intervention. This dynamic allocation prevents downtime for either device and ensures that both remain ready for operation when needed. This is particularly valuable for businesses or facilities where both Tesla EVs and multiple Optimus Gen 3.5 units operate simultaneously. A factory floor equipped with a fleet of Tesla delivery vans and a team of Optimus robots can avoid bottlenecks in charging schedules. Instead of competing for limited power resources, the intelligent management system orchestrates a smooth energy flow, charging some robots while EVs are idle, then switching focus when vehicles require more power for upcoming trips. Another key advantage lies in load balancing. By analyzing grid demand in real time, the system can schedule charging sessions during off-peak hours, reducing electricity costs while avoiding strain on local infrastructure. This approach mirrors Tesla's time-based control feature for EV charging, now extended to cover robots. The system's AI-driven algorithms learn user routines and predict when each device will require energy, further improving efficiency. For households, the integration with Tesla's Powerwall and solar roof adds another layer of autonomy. Solar-generated electricity can be allocated between the EV and Optimus Gen 3.5 according to priority settings. If the household's daily needs are modest, but the robot is scheduled for intensive cleaning or heavy lifting tasks, the majority of solar energy can be diverted to the robot. Conversely, if a long road trip is planned, the system can preemptively shift more energy toward the vehicle in the days leading up to departure. The technology also offers safety benefits. By intelligently controlling the charging sequence, it prevents both the EV and the robot from drawing maximum current at the same time, reducing risks of circuit overload. Additionally, continuous monitoring allows the system to detect abnormalities in charging behavior, such as unexpected voltage drops, and take corrective action before they escalate into hardware damage. We appreciate your contributions and hope you will have the most relaxing feelings after watching this video. If you did, please hit the like button and join the Techno Creator family by subscribing to our channel. And don't miss out on any of our awesome videos by hitting the bell icon. We value your feedback and your time. Thank you so much for watching, and we'll see you soon. Until then, stay safe and have fun.